So, we have been looking into the fatigue damage of marine structures. There initially we said if the time series of the stress cycle is available, where the amplitude of the stress remains constant, then one can say that n can be for the SN curve is simply A S minus m, and the fatigue damage can be simply n by n, and so on. As we know that the stress cycle with a constant amplitude does not remain in marine structures because of the dynamic effects caused on structures, then we have discussed about the spectral analysis, where we said find out the 0th and the second moment of the stress cycle spectrum, then as a simplification replace the constant amplitude with sigma EFR, where EFR is the effective fatigue stress range, which is given by a simple expression in the effective fatigue stress range gamma function of m plus 2 by 2 raised to the power of 1 by m plus 2 by m raised to the power of 1 by m. Once you know this, again you can find the fatigue damage d is simply n by n, where in my case now n will be A, instead of S I will use sigma EFR to the power minus m. So, in that case d becomes n A sig. This is for all C states. You may wonder that how this equivalent effective fatigue stress range is representing all C states, though it is a constant amplitude which is having equivalent value of effective stress range. This is accounting for the spectral moments which has been taken from the stress cycle spectrum. So, this single value represents equivalent fatigue stress range, which is now applicable to all the C states. Now, if you really wanted to find what we call fatigue life in years, you can easily find inverse of this. Where D is calculated for the period of 1 year. Now, this is true, this exercise is true when the stress cycle spectrum remains narrowband. So, I should say for narrow banded spectrum the above procedure is okay. But if it is broadband, then how do we handle this? The spectrum is broadbanded, then how do we handle this? There are many methods available. To treat, I should say, to treat the broadbanded spectrum. Now, what kind of treatment it is giving? It is trying to convert the spectrum into an equivalent narrowband spectrum. So, we call these as correction factors. Now, let us see how they are handled. Let us try to draw a typical broadband spectrum and see what correction factors or what different methods are applicable to treat them into converting them into a narrowband spectrum. Let us say a typical broadband spectrum looks like this, which I am drawing here. Let us say this is my typical example of a broadband spectrum. Now, there are three methods available which is commonly applied in the literature for treating this kind of broadband spectrum. Let us see what are they. First could be the conventional rain flow count. The moment you hear this name rain flow count, you have already remembered that this is a technical or traditional method available and applied to peaks and valleys, which we saw in the time series of the stress cycles, where we used it to find out the fatigue damage estimate. But let us see how I will modify this to use it for a broadband spectrum like this, because there are no specific peaks and valleys, because for this there is no valley, for this peak there is a valley, for this peak trough both are trough, etc. It is very difficult to identify the successive peaks and valleys. Okay. So, let us see how we will handle this. The second method is upper bound method. The third one is the lower bound method. In the rain flow count method, largest cycles are first extracted. So, largest cycles means, let us say look for the maximum peak and maximum trough. These are first extracted from the figure. Then the smaller cycles are considered as superimposed onto the larger cycle. This method is considered to be the most reliable technique for fatigue damage estimates. So, look at the maximum range, then subsequently you can look for the smaller ranges. This is a smaller range, this can be another smaller range, and so on. So, all these are superimposed on the larger range and use that as a rain flow count technique to find out the fatigue damage estimates. Now, if you look at the next technique, which is the upper bound method, in this case look for the peaks in crust and their matching peaks in trough and form a pair. Let us say, what does it mean? Let us say in this case I can say that this and this are approximately matching. So, this can be one cycle, and you can say this value and this value, that is the peak in the crust and the peak in the trough or matching. This can be one case. So, keep on grouping them. Okay. So, peaks in the crust and their matching peaks in the trough are grouped, and then you can do the cycle counting and do the fatigue damage estimate. In this case, look for the successive peaks of crust and trough, that is, look for this, look for this. These are successive values. You can see there is a peak and then there is a trough. Similarly, there is a peak and then there is a trough, and so on. So, keep on grouping them. So, it is estimated that this will give me the lower bound count of the fatigue damage, this will give me the upper bound count of the fatigue damage. This is the most reliable method which can give me the fatigue damage estimates correctly. Okay. So, if I got a broadband spectrum like this, I can try to group the peaks of the values or the maxima and minima or the peaks of the crust and peaks of the trough in this three manner, and then try to estimate the fatigue damage by the following method. As I said, once I do this, I would like to convert the given broadband spectrum to an equivalent narrowband spectrum, because this will help me to use the existing narrowband spectrum equations available to me for fatigue damage. I will apply a correction factor to this suggested by various researchers. Now, all the three methods have a basic problem. There is a basic difficulty in all the three methods. None of these methods has definition of cycle, because as I said, keep on picking up the largest peak in the crust and the largest peak in the trough. Okay. So, you are picking only the maximum values at the amplitudes, but the cycle is not concerned. you can see in this example the cycle is well spread. Okay. So, none of these methods has definition. Okay, let us put it like this, none of these methods define the cycle of the measurement amenable amenable with the standard statistical analysis. Hence, the frequency content are not possible because the cycle or the time cycle is not defined. We pick up only the amplitudes, we do not have any control on the time cycle. Okay. Therefore, how to handle this problem? So, now the spectral fatigue damage assumes that the structure subjected to random loading has the signal as stationary Gaussian and random. This is a very famous assumption which has been established by Rice and Bendit in early 60s. According to this, the results of the analysis will be produced for a mean period of 0 crossing per unit time. We already have a classical definition for 0 period mean crossing per unit time, which we said this is equal to m0. I will call this equation number 1. Now, in the similar terms, the mean period of crossings of mean period between crust peaks or trough peaks per unit time is given by T suffix c, I am using crust here, root of m2 by m4. These are true when the given narrowband process is stationary, is Gaussian and pure random in nature. Okay? I call this equation number 2. Now, I have 0th moment to be computed for the stress cycle spectrum, second moment and fourth moment. In general, we already have an equation to compute the nth moment. The nth moment is given by mn zero to infinity fn s sigma sigma f df. As a general equation. So, you can find 0th moment, second moment and fourth moment using this expression for a given spectrum where f is in hertz and s sigma sigma is the y axis of the spectrum. Here f is in hertz. And S sigma sigma f is one sided spectrum. Okay? That is why the half is not there. So, one can obtain mn values by also by numerical integration. If you are not able to integrate it for a given domain, you can use numerical integration technique and find mn values for n varies for 0, 1, 2, 3, 4 etc. Having defined the 0 mean crossing period Tz and the mean period between the crust peaks or the trough peaks as Tc, I define now an irregularity factor beta is now defined. Beta with an irregularity factor is the ratio of these two periods, equation number 4. Beta is a very important parameter in estimating the fatigue damage. When the stress cycle range is very large. The values of beta lies between zero and 1. Let us see what 0 means and what 1 means. As beta approaches 1, the irregularity factor approaches 1, what will happen? Tz will become Tc. As beta approaches 1 unity, the signal will become a regular sinusoidal signal. So, at this wave or at this stage, the spectrum will become narrow banded and the probability density function of the stress range will become Rayleigh distribution. So, I can write the probability distribution function of the stress range of the peak. So, I should say PDF of sigma p peaks, I am talking only about the peaks, is now a standard equation of Rayleigh distribution, which is sigma p by m naught exponential of minus sigma p square by 2 m naught, equation number 5. So, when beta approaches 1, the cycle counting becomes simple, is it not? The basic problem what we had in the broadband spectrum is cycle counting, right. We are not having difficulty in identifying the peaks and troughs, that we have already done. Now, how to count the cycle, because I cannot use it in the frequency domain because cycle counting is not clear. So, when beta becomes 1 by introducing an irregularity factor, as you see here is a ratio of the time periods between the crests or the troughs with that of the 0 mean crossing periods of the stress cycle, the signal will get converted to a regular sinusoidal signal. For that, the spectrum will become narrow banded and the cycle counting becomes easy. Okay. When beta approaches 0, I shall say this case A. So, let us say when beta approaches 0, it is not 0, it is approaching 0, close to 0, signal will become more like a white noise. In this case, the signal will become wide band or broadband, and the probability density function of stress becomes Gaussian. It will follow Gaussian distribution, not Rayleigh. In that case, probability distribution function of the peak will be given by a different equation, which is standard Gaussian equation 2 pi m naught exponential of minus sigma p square by 2 m naught. Let us use bracket here also because there is a negative sign here. So, let us say equation number 6. But in reality, the signal is neither narrow banded nor wideband. That is, beta is not equal to 0 equal to 1. So, it lies in between. In that case, how do we handle this? Okay. If case A and B are valid, then I can easily use probability density function directly. I can easily find out the fatigue damage, spectral fatigue damage. But when beta is, when it is neither narrow banded nor wide banded, how do we handle this problem? In such cases, correction factors are applied to convert, I should say, the signal to an equivalent narrow band form. Okay. So, people can convert this into an equivalent narrow band form. Now, one can be happy to know that once I convert this to a narrow band form, all my equations available for a narrow band form, which we discussed in the last lecture, can be directly applied. So, I can easily find out the equivalent fatigue stress range sigma EFR and try to find out the fatigue damage by the equation which we discussed in the last lectures, or the fatigue live estimates. So, now I must have a correction factor applied to the existing signal to convert that to an equivalent narrow band. Okay. So, there is an idealization here. Now, many researchers attempted this. Technique and recommended various correction factors so all these correction factors attempts to correct the fatigue damage estimates of narrow band spectrum to account for the broadband. Okay. So, the correction is not applied on broadband, the correction is applied on the calculations made on the narrow band. Okay. So, that correction will take care of the conversion of the broadband to narrow band, right. So, very briefly we will not get into the methodology of these are all empirical relationships. Let us quickly understand how they have been done, okay, before we look into what they have done. Various samples of time histories are generated. These are the steps what people have followed in arriving at the correction factors. Various samples of time histories are generated for the stress spectrum. From the time history, using inverse Fourier transforms, they have obtained the conventional rainflow count. They have obtained the conventional rainflow count, and based on which they have given the correction factors to predict the fatigue damage. There are many of them, but we will see only few of them. The first one is given by Wirschings, named after him, correction factor Wirsching pH and light MC 1980. Fatigue under wide band random loading, Journal of Structural Engineering Division, ASCE, 1593 1607. That is a reference where this Wirsching's correction factor is being borrowed. He says that the damage estimate based on the rainflow count, the rainflow count is modified by an equation which is given for the damage estimate for the narrow band multiplied by a factor lambda, which is a function of mn epsilon. Can you give me the equation number here? 6, 7, yeah, that is what, okay. Whereas DRF is the rainflow count damage, DRF is the rainflow count damage, DNB is the damage estimate based on narrow band damage, narrow band damage means damage based on the narrow band equations, and lambda ME m epsilon is given by an empirical value which is function of AM plus 1 minus AM 1 minus epsilon to the power CFM. Equation number 8, where A of m is again an empirical equation suggested by the researchers, 0.926 minus 0.333 m. I will always request the viewers to look into all these original equations from the paper, okay. Though I am trying to reproduce here for the benefit of the viewers so that you get at one hand all the equations, but still you must always look into the original reference and check whether they are all right. AM C of m, where m is the slope of the ascent curve, okay, that we already know, 1.587 m minus 2.323, and epsilon is root of 1 minus beta square, and what is beta? No, reliability, reliability is the last unit. No, beta. Turn back, we just now discussed beta. What is beta called?
Fatigue damage.
What? It's called adjustment factor. Okay, we are trying to apply this. So epsilon is 1 minus beta square. Beta is the ratio of proportion of Tc versus Tz, and Am and Cm are empirical values given. So I know the lambda, I correct it for different m slope of the curve and try to find the modified damage of rainflow count when I know the damage from the narrow band. This equation is already known to me in the last lecture. Alternatively, another researcher made a different solution. Cam and Dover give a different approach. Institution of Civil Engineers, Part 2, '87, 539, 556. So Cam and Dover made a different approach for this problem. They used the equivalent fatigue stress range, which is stress EFR. The whole idea was to conceive to look at the cumulative fatigue damage under an equivalent constant amplitude stress cycle. Or I should say stress range extracted from the rainflow count. He says sigma EFR is integral of 0 to infinity sigma, the stress range to the power m, the prob density function of sigma r dr, equation number 10, because those constants were 9. A of m and C of m were 9. Alternatively, sigma EFR can also be given by, that is nothing but 8 m naught root, okay, 8 m naught root, we already have this, lambda of m epsilon is the same correction factor with the gamma function m by 2 plus 1 raised to the power of 1 by m. The third equation was proposed by Chowdhury and Doe. The constants were 9, this is 10 and 11. Fatigue analysis of offshore platforms. Subjected to sea wave loading. International Journal of Fatigue, so their study is based on the distribution of the peak. Peak distribution in different sea state spectra. They say the equivalent fatigue stress range can be given by 2 root m naught epsilon m plus 2 by 2 pi to root pi gamma of m by 2 plus 1 this is m plus 1 by 2 plus beta by 2 of gamma of m plus 2 by 2 plus error function of beta by 2 of gamma of m plus by 2 the whole raised to the power of 1 by m. So, they have modified the expression for the equivalent fatigue stress range with an error function, whereas epsilon is as same as you had in the last equation. As 1 minus beta square. So, the error function of beta is given by an empirical relationship again .3012 beta the value of beta varies from 0.13 to 0.96, that is the range, which is very valid for an offshore structure. So, in this lecture we have discussed how a broadband or wideband spectrum of the stress cycle time history can be handled to estimate the fatigue damage by converting this or by applying a correction factor, which is called an adjustment factor, to the values of the damage estimate made by narrowband spectrum calculations to account for the widebandedness or the broadband nature of the spectrum in the fatigue damage estimates. In reality, because in reality the spectrum is neither narrowbanded nor widebanded, it is a mixture. So, we apply a correction factor or an adjustment factor which is applied on to the calculations, and we have seen 3 approximate procedures suggested by different researchers in the literature, which will help us to estimate the equivalent fatigue damage of a broadband spectrum based on the estimates done on the narrowband spectrum, whose equations are already available to us in the last lecture. Okay. In the next lecture we will discuss about the continuation of this and talk about more important parameter called stress concentration factors and their link with fatigue damage. How are they linked? Any questions here? Okay, thank you.